Good morning, students. I'm Dr. Soumyajit Ghosh. In today's presentation, I'm going to discuss about the conformational analysis of N-butane. As you know that the molecular formula of N-butane is CH3, CH2, CH2, CH3. Now, this is carbon number 1, 2, 3, 4. So you can see here one single bond between the C2, C3. So if we consider one neutral axis passing through this single bond, so we'll see that whatever the substituent at C2 and C3, like methyl, hydrogen, hydrogen, they are symmetric to each other. So there is a possibility of free rotation of this single bond. And without breaking this bond, these substituents can rotate. As a result of free rotation of C2-C3 bond, so there can be the different spatial arrangement of methyl with respect to the hydrogen. So if we consider, if we fix the C2 and if I do the free rotation of this single bond, so this methyl, hydrogen, hydrogen, they will change their position. So some conformations are preferred conformation. Due to the free rotation of this single bond, some conformations will be preferred orientation. So they are referred as a conformers, or we can call it as a rotamers. So due to the different conformer, the physical and chemical properties may change. The analysis of N-butane. Due to the free rotation, how many different types of conformation we can get? So we'll see that due to the free rotation of this C2-C3 bond. So this is the Newman projection of N-butane. We can see this is a frontal carbon atom. So frontal carbon atom, we can see that methyl, hydrogen, hydrogen. And this red circle, this is the backside carbon atom. This we can call it as a C3. If this one is C2, then this red circle is C3. So C3 also substituent are there, methyl, hydrogen, hydrogen. So because of the Newman position, we cannot see the single bond between the C2 and C3. But due to the free rotation, what will happen? This methyl will change, hydrogen will change, and this hydrogen also will rotate. So there will be the scenario where the relative position of this methyl, this C2 substituent and C3 substituent will change continuously. So we'll do the conformation analysis of N-butane due to the rotation, what type of conformation we can get, and due to the arrangement or orientation of the methyl groups, which conformations get more stabilized with respect to other. So that analysis is known as conformational analysis of N-butane. In the subsequent slides, we'll see due to the rotation, what type of conformations or rotamers we'll get. So the conformational isomerism is a form of stereoisomerism in which the isomers can be interconverted just by rotations about formally single bond. So if we see here that this is the N-butane, CH3, CH2, CH2, CH2. So this is a single bond. So due to the free rotation of this single bond, the different orientation we can get it. So this is the staggered conformation. In the staggered conformation, we can see here, and this is the Newman projection. So this is the frontal carbon atom. We can see that hydrogen, hydrogen, methyl. And the backside carbon atom, methyl, hydrogen, hydrogen. So if we can see this methyl at the frontal carbon atom is in between the two hydrogen of the backside carbon atom. Again, this hydrogen is in between hydrogen and methyl. This hydrogen is in between methyl and hydrogen. So, if we call it as a dihedral angle, that means with respect to this methyl carbon, so methyl carbon and this backside carbon, if we consider the one plane, and this methyl carbon, this backside carbon and this frontal carbon, if we consider the plane, the angle between these two planes, in this case we can see 180 degree. 180 degree. So this methyl and this methyl, they are in anti-periplanar orientation, exactly opposite to each other. This C2 methyl and C3 methyl, they are anti-periplanar orientation. So it is a most stable conformation. We call it as a staggered conformation. So first of all, they are the in-between of the substituent at neighboring carbon atom, and also this methyl and this methyl, they are exactly opposite to each other. They are trans to each other, or we can call it as an anti-periplanar orientation. So we can call it as a staggered conformation. And eclipse conformation means that when the C2 substituent and C3 substituent, they are face to face. Here it is in between. Okay, so that is why we call it as a stagger. But here we can see that this methyl and this methyl, they are in the straight line. This hydrogen, they are in the straight line. This hydrogen, they are in the same line. Okay, so they are face to face. So because the face to face interaction or close proximity, definitely steric repulsion will be there, and that is why this conformation will be, energy will be high, little bit destabilized, because these substituent, they are face to face. Okay, although they are C2 and C3, but due to the close proximity, we can call it as a eclipse conformation. So that means they are in the face to face or straight line. They are the straight line. They are in the straight line. But here we can see that hydrogen is in between hydrogen and methyl. So if we call it as, this is a 60 degree, this is a 60 degree, and this is a 60 degree, right? So total is 180 degree. So because the substituents are in between the substituents of the backside carbon atom, that is why it is a staggered conformation. And because it is in between, somehow the repulsion is dissipated or reduced. Okay, but because of the close proximity, the repulsion is more high. Okay, so that is why this is eclipse conformation and this is staggered conformation. And staggered and eclipse also can be the defined conformation. We'll see in the subsequent slides. Now we'll do the conformational analysis in detail. So this is a staggered anti. Staggered, you can understand that this C2 and C3 substituent, they are in between. For example, this is C2, hydrogen, hydrogen, methyl. So this hydrogen is in between hydrogen and methyl. This hydrogen is in between methyl and hydrogen. This methyl is between hydrogen and hydrogen. Moreover, this methyl and this methyl, they are anti. That is why we call it as a staggered anti-conformation, and we call it as a 1. Okay, and what is the dihedral angle? Dihedral angle, I told, this methyl carbon atom, this carbon and this carbon, if we consider one plane passing through these 3 carbon atom and another plane passing through this carbon, backside carbon and frontal carbon. So the angle between these 2 planes. Here in this case, what is the dihedral angle? 180 degree. So now we'll rotate 60 degree. As I told that C2 and C3, there is a free rotation is possible. So one thing we can do, the frontal carbon substituent will remain fixed. Only the backside carbon atom will change it. So this methyl will come here, this hydrogen will come here, this hydrogen will come here, and you will get the eclipse conformation. As I told, eclipse is little bit destabilized because of the close proximity. We can see methyl and hydrogen. methyl and hydrogen, hydrogen and hydrogen. But meanwhile, the dihedral angle is now 120 degree. You see 120 degree. This is a 120 degree. Again, you do the 60-degree rotation. 60-degree rotation, then this methyl will come here. This hydrogen will come here. Okay, and this hydrogen will come here. So you will get staggered. So there is a name of this staggered conformation. Because of this methyl and methyl very close, okay, that means C2 methyl and C3 methyl, their dihedral angle is 60 degree. So we call it as a staggered Gaussian conformation. Okay. So if I compare the stability between these 1 and 3, which one will be more stable? Definitely 1, because this methyl and this methyl, they are anti-orientation. This is also staggered. This is also staggered. But in this staggered conformation, this methyl and methyl, they are close. That is why we call it as a Gaussian conformation. Again, if you rotate 60 degree, what will happen? This methyl will come here, this hydrogen will come here, this hydrogen will come here. So you will get the total eclipse conformation. So in this case, methyl methyl, they are face to face, hydrogen hydrogen and hydrogen hydrogen. And because of methyl methyl, what will happen? It will lead to the enormous steric repulsion because of the close proximity. But in this case, in this conformation, the dihedral angle is 0 degree. Again, you rotate 60 degree, what will happen? This methyl will come here, hydrogen will be here, hydrogen will be here, and you will get the staggered Gaussian. And this 5 and 3, they are equivalent. Only in this case, in the right hand side, here it goes to left hand side. But they are equivalent. Okay. Conformationally equivalent, energetically equivalent also. Again, if you rotate 60 degree, this methyl will come here, hydrogen will come here, and this hydrogen will come here. So you will get the eclipse conformation, what we call it as a 6. And this eclipse, this steric repulsion between methyl hydrogen and here hydrogen hydrogen and here methyl hydrogen. So again, if you rotate 60 degree, you will get the staggered anti-conformation. So basically, if you rotate 60, 60, 60, so you will get alternatively eclipse and staggered conformation, and also the staggered anti is the most stable conformation. Between the staggered conformation, the staggered anti is more stable compared to the Gaussian because of the farthest position of the methyl groups. And among the eclipse conformation, this eclipse conformation where methyl methyl are very close, these are most destabilized. Okay, these eclipses are little bit stabilized. Okay, and overall eclipse staggered conformation is energetically favored with respect to the eclipse conformation. When we see the energy stability, we can understand because of the position. One thing I want to tell that although you are rotating 60 degree, in between also conformation is possible, like 5 degree or 10 degree, 11 degree, 12 degree, like that. So, but those are energetically not favored structure or not favored conformation. Those conformation, we call it as a skew conformation. So we are not dealing with the skew conformation because they are energetically not favored. So only that is why our concern is that rotating 60 degree, whatever the conformations we are getting, with that conformations or conformers, we will do the analysis. And these are called the rotamers as well. So you can see here the skew conformations are infinite conformations in between the specific ones formed due to the rotation along the bond, but they are not anti-staggered or Gaussian. So if we can see here, in the case of totally eclipse, the dihedral angle is 0 degree. Okay, and then here another eclipse where this methyl and hydrogen. So the dihedral angle is 120 degree. These are staggered conformation, these two. But in this staggered, it is called as a Gaussian because the dihedral angle is 60 degree. Always we have to see that the angle between the methyl and methyl. What is the angle? That is the dihedral angle. So basically, here the 60°, and here because of the anti-periplanar orientation, this is 180°. So if we see the stability, which is more stable, first of all I told that between staggered and eclipse, staggered conformation is more stable. Eclipse is high, okay, high in energy. So if we consider the relative stability, most stable conformation is this one, this. First of all, it is a staggered, and second is this methyl and this methyl, they are the anti-orientation. Next is Gauche. We can put as a number 2. This is staggered. Somehow the repulsion is dissipated, reduced, and also at the same time, because the dihedral angle, some sort of repulsion exists because of the close proximity. So order of stability is 2. So staggered conformation is done. Now we move to the eclipse. Eclipse, we have to see that this is the number 3. Okay, stability, it is more stable, then next, and then next eclipse. Why eclipse? This one, because there is a methyl hydrogen interaction. Methyl hydrogen interaction, although the dihedral angle is 120°. And least stable is this one, totally eclipse. That means the dihedral angle 0°. Here methyl group is relatively bulky than hydrogen. So methyl interaction, the steric repulsion or steric interaction is high, and that makes it unfavored conformation. So least stable is number 4. So this is the order of stability of the conformations. So as we discussed in the previous slide that we have analyzed, that this is the order of stability of conformation of N-butane. This is the anti is more stable than Gauche, then eclipse where methyl hydrogen, that means the dihedral angle is 120°, and the least stable is the totally eclipse. Totally eclipse, the dihedral angle is 0°. Okay, so this is the order of stability. This is more stable, this is the least stable. Okay. Now in this slide, if we see the energy versus dihedral angle for butane. Okay, so we can see this diagram. Okay, this diagram. So this is, we can call it as a crest. This is a trough. So trough position is always occupied by the staggered conformation. Okay, this one. Okay, and this crest, the mountain top, these are always occupied by eclipse conformation. Now you can see here which is most stable conformation, staggered conformation, and anti. So that is why I have written 180°. Dihedral angle is 180° because it is most stable conformation. Then again it will go to the this one, eclipse. Eclipse is unstable conformation, but here methyl hydrogen, that is why this is 2. Then again it will go to the staggered but Gauche. Okay, Gauche conformation. Meanwhile, 180°, 120°, this is 60°. 60°, this is 60° dihedral angle. In this case, it was 120°. Okay, 120°. So, because of the close proximity, these 3 is little bit unstable or energetically unfavored. 1 is most energetically favored. Then 3 to 4, the dihedral angle 0°. Why? Because we have to see the methyl that angle. So they are in the face to face, they are in the straight line. Here hydrogen straight line, hydrogen straight line. So this is the most unstable conformation or energetically unfavored conformation. This is the totally eclipsed conformation, and the dihedral angle is 0°. And here the steric repulsion is the highest extent. So that makes this conformation most energetically unfavored conformation. Then again, if you rotate 60°, you will get the conformation 5. Okay, so this is a staggered Gauche. Then again the eclipse conformation, and again lastly the staggered anti. So 180 will start, 120, 60, 0, 60, 120, again 180. One cycle is complete. So if you see here, 1, 3, 5, and again 1. So 1, 3, 5, these are all staggered, but because of anti it is the most stable. And among the 2, 4, 6, 2 all are eclipsed, but the 4 is most answered because of the total eclipse conformation. So that is why this diagram looks like this. So if we consider this as a baseline, that most favored conformation anti as a baseline, so with respect to this, the eclipsed conformation 2 or 6, the energy difference is 4 kilocalorie per mole. 4 kilocalorie per mole. And from this baseline, the total eclipse conformation, the energy difference is 6 kilocalorie per mole. Okay, 6 kilocalorie per mole. And from this baseline to the Gauche conformation, that energy difference is 0.9 kilocalorie per mole. Okay, so we have seen that energy versus dihedral angle for in butane, and from the steric repulsion of the methyl groups we can understand that what the diagram looks like and what is the order of stability of the different conformations or rotamers. Thank you.